A really nice example of relativistic effects in action is in our GPS satellites. There is a measurable difference in the time that they measure compared to the clocks back on Earth. So this is a really wonderful example to have a look at. We're told that the time difference in a 24-hour period between the clock and the orbiting satellite is not 0, but it's 0.000038 seconds. Hopefully I said enough zeros there. Have a read of the rest of the preamble too. This is a very wordy start to the question. So, we're assuming that the time difference is due to special relativity, which one or more. Now, just so you know, in previous exams, this one's from 2007, it was possible to have multiple choice questions with one or more answers. In our current study design, not possible, but I still think it's worthy looking at here to really make sure we're stretching our brain. Okay, so it says, first option, the GPS receiver measures the satellite clock running as the same rate as itself. Well, that's not true. One of them will be measuring a dilated time, and one of them will be measuring a proper time. So the GPS receiver on Earth is seeing the satellite moving, so it cannot measure the proper time there. It's going to measure the dilated time. So option B, the GPS receiver measures the satellite clock running more slowly than itself. Well, that's true. That's what we observed. We noticed that difference in the clocks there. Let's check options C and D. GPS receiver measures the satellite clock is running faster. No, we're only ever going to be looking at situations where someone will observe a clock running more slowly than themselves. We won't see people moving in fast motion. Last one. The orbit radius of the satellite is shortened due to relativity. We're going to learn more about this when we do length contraction next, but it turns out that the radius being perpendicular to the path of the orbit actually doesn't have anything called length contraction occurring. So this is not an answer, and you'll understand more a little later on. Okay, we're told we've got an Earth-like planet. There's a hypothetical mission to this planet. The planet is 1.0 by 10 to the 8 meters away from Earth. That's a very big distance. Spaceship is suggested for the mission and it can travel at an average speed of 0.99 c. Don't currently have any technology that does that, but wonderful for these people. Very kindly, they've told us the gamma value, the Lorentz factor value, is 7.1. So that's one thing that's not on your to-do list with this question. They've already given you an answer that they want you to use, probably because they can't be bothered dealing with students with rounded answers, which is fine. Scientists are concerned about the length of time passengers would have to spend on the spaceship to travel to this planet. Use principles of special relativity to estimate the time in years as measured on the spaceship. We're going to approach this question in a slightly different way. We're going to look at it from the scientist's perspective, and then we're going to look at it from the spaceship people's perspective. Spaceship people. Astronauts? I don't know. So from the Earth's frame of reference, the scientists on Earth, they measure the distance to the planet to be, as I put in the diagram, and they measure they know the speed of the rocket to be 0.99 c relative to them. So let's go ahead and figure out how much time, according to the Earth's frame of reference, keeping in mind they ask for it in years, to see why the scientists are concerned. So for this, because we're not accelerating, we can just use time is distance over speed or velocity. You could use displacement over velocity. So the distance, 1.0 by 10 to the 18 over the speed, 0.99 times 3 by 10 to the 8. Okay, remember it gives us our answer in seconds. Let's put this in years. So seconds to minutes, minutes to hours, hours to days, days to years. Okay, so we get 100.6 let's include a few extra decimal places, 76, ... I'm not rounding it off, I'm just cutting it off. 106.76 years. Now, let's figure out what the time is in the spacecraft, what the spacecraft measures as time. Because they are within the spacecraft, they are measuring the proper time. So the proper time is T0. So let's use T equals T0 gamma. Again, they've given us gamma. How nice. We don't need to do that. So rearranging, T0 is going to be T on gamma. So we've got the 106.76 ... and we're dividing it by... Awesome. So, from the astronaut's perspective, whoever's on the spacecraft, they measure the proper time. That's the time measured stationary to the event, so within the rocket's frame of reference. So they only see this to be 15 years. We need to do it to 2 sig figs, so that is fine. Now note, I use years in this here. If you use years for the dilated time, and years will be spat out for the proper time there. So that's perfectly fine. So to 2 sig figs, 15 years. That's much better. From the people in the spacecraft's perspective, they don't understand what the scientists are going on about. They only measure the trip to be 15 years long. So luckily it's not longer than the average human lifespan. Something really important to know in the next question is that light years is not a measure of time. Light years are a measure of length. A light year is defined as the distance travelled by light in 1 year. So when we say we've got a spaceship travelling from Earth to a star system, it's located 10.5 light years from Earth, that is a distance measurement here. If the spacecraft travels at 0.85 c, very kindly they've told us the value of gamma again. We've also got that velocity if we need it. We need to determine the duration of the flight as measured by the astronauts on the spaceship travelling to this particular star system. We're going to take 1 light year. Oh, they've very kindly told us that distance in case we need it. We don't need it for this particular portion of the question, but we would need it in question 18, I think. Okay, so we're eventually going to be using t equals t0 times gamma, but we need a value of t. We can use that length that we did mention now that I think about it. We know this is the distance travelled by the light, and we know the velocity the light was travelling, so we can use that to figure out how long that is measured from Earth. That is going to be this value of t. You might like to label that as t Earth. T0 is going to be the value on the spaceship. Remember, that is a clock that is stationary with respect to the spaceship, so it's measuring the time in the spaceship. That would be the proper time in this circumstance. So to figure out for the Earth, t is going to be the distance travelled, 10.5 light years, divided by 0.85. So if we know it's 10.5 light years, that's the distance travelled by light in 1 year, and it's 0.85 times the speed of light, that actually tells us the value of t in years, which is about 12.35 years. And that's the time measured on Earth, but we are interested in the time measured in the spaceship, measured by the astronauts on the spaceship. So that's t0. Like we saw previously, rearranging, that's t on gamma. So we're really hoping for the astronauts' benefit that they are measuring a shorter time. Otherwise, they're going to be very bored in space. So let's do that 12.35-ish years divided by the value of gamma, 1.90. So as always, I keep my previous answer in the calculator. So divided by 1.90, don't need the 0. Okay, 6.5. Do we need to do it to 2 sig figs? Yes. So 6.5 years. Ooh, that's so much better for those astronauts.